Robert Berke. He's the CTO and a co-founder at Kaiko. And I'll give us a quick intro. I mean, we're very happy to be working with Kaiko. They're working, the part I'm most impressed with is they're working with the NKMI, the Netherlands Kanker Institute. Hopefully he's going to mention something about that. And it's actually, in terms of physical size of the configuration from NVIDIA they're running, it's one of the largest in Holland, if not the largest, trainings up to 2 hours. So I'm sure we're going to hear all about that, and I'll hand it over to Robert.
Thank you very much, Bam, for the introduction and also for inviting me here, giving me the opportunity to talk a bit about what we are doing at Kaiko. And my talk is a bit set up such that you can also view this not only about our story, but it's a general recipe to build what we are building. And I'm going to talk you into that first, a quick intro on what we are building. But let me set the stage. So this talk is about building a multimodal foundation models in oncology, and our whole spectrum going from very early research to then clinical deployment of these foundation models. And since we are focusing on oncology, I also want to set the stage that this is extremely complex disease, of course. So here there's a quote: "To confront cancer is to encounter parallel species, one perhaps more adapted to survival than even we are." So it's an extremely complex problem, and we are trying to get more help via AI. And let me quickly give a bit of an intro on who we are. So founded in 2021, we have 2 offices, one in Amsterdam, directly at the Netherlands Cancer Institute, and one in Zurich, where I'm based. And we have this strategic partnership with the Netherlands Cancer Institute. It's from day one, we are actually, our Amsterdam office being at the institute, we were able to sit with the doctors, with researchers, to see, okay, what should we really build here? And it was before the big AI hype, and we were just extremely lucky to get started and right away jump into that hype. So we take that really in a very ambitious way. So we grew in this 3.5 years to more than 70 people now, and so far a huge tech focus. Yeah, so we have more than 40 ML engineers on top, DevOps, infrastructure, and so on. So we do little external work, so to say, to advertise what we're doing. So this is one of the rare opportunities so far, but that's also coming. So and we're planning to expand to other hospitals, but at the moment, still, I would say 95% of our focus is really at one hospital, at the Netherlands Cancer Institute, to make sure that we are not spreading too thin all resources in there. And since last summer, we are working with Nibble as well. That is a huge boost for us. I'll talk a bit more about that. So what do we build? So we built a domain-specific AI assistant for oncology. So that is multidisciplinary. So we are not focusing on pathology or on radiology, but it's really going across all the disciplines. And eventually it should come to the expert level, so that actually, so this is a tool for the medical experts. There are tools around that are already being used, AI, namely one prominent one is actually ChatGPT. So we listened a bit around, talked to clinicians, and think there's actually, it is at least where we listen, so we think it's more than 50% that is actually already using something that's not really designed to be used in the clinic, but also it's, of course, no surprise. These tools, you use them at home, right? You use ChatGPT and you don't want to go to work and then all of a sudden, okay, now I'm less supported basically as at home. So you, of course, start using it. So, and what does use mean? So there's often, it's very general advices or rare cases. I don't mean rare cancer cases, but rare, something you didn't encounter for a while and you want to get reminded. Also, data structuring is a very usual thing that happens in ChatGPT. And But there's of course concerns. There's usually people use the private subscription, not the company enterprise subscription. Data privacy could be an issue. So what happens? So these results are not validated. They're not. Are they trustable? I think we can trust the clinicians. They still know. Okay, if that was a hallucination, I know that's okay. Ultimately, I think there will be guidelines developed on how to use these sort of ChatGPTs and alikes in the clinic. But what I want to present here is actually our effort, where we're trying to build something that is much more useful. And it is more useful because it's trained, starts with a few components. So here this cycle really shows the 5 steps, so to say, to build this. That's the recipe. And it, of course, always starts with the data. So for us, it's a multimodal endeavor. We started at the Netherlands Cancer Institute building a cloud data platform. So get all the data out of the clinical systems into a cloud data platform that is owned by the NKI. So it's a tenant owned by the NKI, but we work together to build this. And I think that's might be really subjective, but I think this is really the state-of-the-art data platform that is deployed at the hospitals in the Netherlands. And yeah, it's by now it's really big. So we have all the data in this clinical data platform. So how much is it? So this is not the NKI specific. This is a general. So if you have, say, 10,000 patients roughly, this is how much you accumulate. So in text, it's not so much. So 100 gigabytes. In imaging, it's huge. It's above petabytes. So here, rough estimate, it's 10 petabytes. And for omics as well. And this will also change rapidly. All these new single cell sequencing, transcriptomics, these new capturing technologies coming, and that's just much, much more data very soon. But sorry, that should say per patient here. So if we look into one patient, then okay, it's really very little text. So 5 megabytes. Imaging is up to 500 gigabytes, and omics is up to 500 gigabytes. So think again about ChatGPT. I mean, you don't want to upload 1 terabyte into ChatGPT. It's not possible, yeah. But you actually want, as a clinician, you want to use such an AI assistant without first loading the data. So it should be somewhat given. That's one thing we solved. The next part is this ChatGPT and the like. These are these LLM architectures, and we think they're not necessarily made for capturing this omics and imaging data very well. So what we do is we still have an LLM component, an open source LLM component. That's on the right side, the reasoning engine. But in the front, we actually put what we call what's called an encoder. So somewhat it's your sensors, or it's the model sensors that are made for the oncology domain. So there's text that really understands that sort of reports best. It's a vision encoder to understand the, as we just heard it in the previous talk, pathology data best, radiology data best, and there's the omics encoder. Once you have that foundation model, then the really cool thing is, and that's really why we doing this, you get this patient representation. So it learns to understand the patient data, basically. For us, it's hard to understand what it learned. But then there's the next step, namely building these downstream tasks, so the applications. And that's now going much, much faster as it used to. And that's really, it's this engine for us that really allows you to build our task very, very quickly. I will come back to that also a bit later. And what's super important is that we're evaluating everything. And so we are not the medical experts. So we collaborate with medical experts in clinical studies, for instance, to check whether it's at the performance, whether you can trust the results and so on. We try to, though, make this at such a massive scale that we also try to automate. So sometimes we can have an LLM judge whether it's good performance or not, at least in the beginning of that evaluation part. And we work on benchmarks that are automated and checked. Validation as well. So again, with the medical experts. So is it actually really useful what we are working on? And the crucial part is also feedback collection. Yeah? So we want that data, whether it's useful, whether it's performing well enough, and we are collecting all these also to later adapt to preferences of doctors. So there could be 5, 6, 7 treatment options, and usually a doctor would maybe use a specific one, and that's in this alignment feedback part. Yeah. Good. The last step is you need to bring it back into the clinic, and that's also a very different requirement. Now we want to update with new data. So this assistant goes through the patient journey from discipline to discipline. There's new data being uploaded, and that needs to come back into the assistant. So when starts with the radiologist often, so there's new images being done, and that need to be in there before it's handed over to someone else. And yeah, at the end, we're actually closing that cycle and come back into the data domain, because we're collecting the feedback, we're collecting everything actually that is run through our model is just stored. And there's a process that we call data refinery that makes it available again for the next training runs. Ultimately, there could be something that this model can actually self-improve. This is very, very far, but we just make sure that at the moment everything is already stored. So again, so on the left side, you get this EHR data, usually, and then the image data and everything together. So on the left side, you have a clinician without an assistant, so to say, and the clinician needs to look for the data in very fragmented different systems. And we have here this our data pool, then the foundation model, and then this is all fed into the AI assistant that is deployed in the clinic. So what it does then is you get very different application all of a sudden. Instead of looking for data and really having data in mind, what you do is you have the actual thing you want in mind. So meaning there's the clinical preparation and you get the structured data as you need it. There's a trial matching and it can just do it depending on how you want to structure it. I'm just making a few examples here. There's you can chat with your documents. I mean, often it's just so much information and you want just a particular one, but you need to find out what it is. So many examples that we are trying to solve here, high level. Just one other point is, okay, so how does that data get into? So you have all this data in the clinical systems. Then we have it in this clinical data pool. And then if there's now the assistant works with one patient in mind. So say here, this clinical preparation looks at PDFs. It gets the information out. So it just loads that PDF of that patient, does the structuring, and gets it into that structured form. And similarly for other parts, so we do this first consult preparation, for instance. So it's a lot of reports, guidelines, everything in there to structure it. We can also jump to parts where we're now taking all these, what I said before, up to a terabyte for a patient data, everything, and then look at the many applications we can do. Exactly. So this requires a lot of training work or a lot of GPUs. And I want to very quickly go into these numbers. So where are we positioned as Kaiko to be able to actually create this foundation model for oncology? So I make it very rough numbers. So we go 1 GPU. That's usually what so far has been done in healthcare AI. So 1 to 10, I would say. If we look at 100 GPUs, then this is what you usually do now in vision transformers. So everything on vision, that's roughly the number. 1,000 GPUs, that's large language model fine-tuning. So it's already a lot. Post-training, so alignment. And then the 10,000 and above, that's the LLM pre-training. And on the inference part as well, so again, clinical models so far usually run on 1 GPU. If you build a clinical assistant, for instance, that is made for medical experts, you would expect maybe ultimately that to serve all of them, it's going to be around 1,000 GPUs. And of course, the serving the general LLMs, that's in this 10,000 GPUs. So it's very rough numbers. So in this 10,000 part, these are the frontier AI labs, Meta, OpenAI, Anthropic, and so on. Recently, DeepSeek showed us, okay, maybe you need less here, but actually we're thinking there's also a different signal. Maybe they showed us how to do this reasoning, fine-tuning, and actually what they've showed is this is really compute intensive. So for us, it's actually more a signal. That's a really cool part that we can do, but it's also, again, in the thousands requirements. So foundation model training, that's this first part. And I'm skipping almost all the details, but just very quickly, there is this thing that is just amazing, and it's called self-supervised learning. So that has such an impact, especially in healthcare, because we can do that. We can train a model and this model now tries to understand the data without any labels. So all of a sudden, you have this massive amount of data that's still, as I described, you need to unlock it physically. But once it's there, you can just throw this immense GPU compute on it. And then the model learns to understand that data. So that gets this recent really scale up in this healthcare AI, where we're working on with 1,000 GPUs rather. Let me skip that for the moment. Yeah, there's all these little details on what we're doing with this in each modality, but I want to quickly say, so on Nebel, we recently, in the last 3 months, actually, we trained a state-of-the-art foundation model, so this vision encoder for pathology. Actually, we just submitted a paper last week about that. So we're basically competing with the best ones here in the world. This recent publication has a very surprising finding for us. Namely, we see that we can be state-of-the-art with 100 times less data on the training run. Now, my message, what I want to convey here is we shouldn't train on less data. It's just, it shows that we are not yet there. We don't yet understand why we're needing so much less data, or put it the other way around. There's still an opportunity to create much, much better models with more data. And we are working on radiology, for instance, have a 3D foundation model here as well. We work on a combined encoder. So there's a lot to do. On the omics part, this is for us a very exotic modality still. So it's the other two, text and vision, somewhat, they work so well together at the moment. Omics is still a bit, will it also speak that same language, namely this patient representation? Do we get it in there? we do some early work on that. It's very experimental still. The field is moving fast, so hopefully we can just also see how others do it and then go with them. And then there's the other part, this reasoning engine. As I said, this is an LLM that we use, an open source LLM, but we're still adapting it. So 2 things. So we do supervised fine-tuning, and that is very compute intensive. At the moment, that's beyond our capacity that we have, GPU capacity, but we have means to bridge it for the moment. But ultimately, we want to go there to have our own capacity in the thousands here. So domain adaptation into medical, that's the one part. And the other part is this reinforcement learning for chain of thought and reasoning that is going to be so extremely helpful for us to do a few things. I will come back into that. I think I'm close to overtime. 5 minutes, okay, good. But the important part is, again, this middle part, this patient representation. Yeah. So if we have that, so this high dimensional embedding, then we can build very fast, very good AI applications that are clinically relevant. And the cool thing is that this representation somewhat works really well with the large language model. So it's not this static thing, but we can actually interact through an LLM with this patient representation back and forth, ask things and so on. So at the end, it's like ChatGPT. You just ask things and it can do a lot of magic things for you. And the better this patient representation and the reason engineering work together, the less work we have to build out new applications. So already now we see there's a lot of things that we can do what's often called a zero shot. So we don't change, we don't need to do anything with the model anymore. It can already do a lot of data structuring part, a few segmentation work and so on. It just works out of the box. And for those where it doesn't work, the more complex task, just name one organ cell segmentation, something like that, we still need to invest more time to train this use based on the foundation model. But the labeling requirements just dropped tremendously. Yeah, so we see this 10% usually that we claim that we still use, but I think often it's just even much less here. I jumped that quickly. That's another slide just showing what sort of task we can do. Let me also jump that for time reasons. But yeah, here the important part is the better the patient representation, the more zero-shot application we will have out of the box. So we really should just move that capabilities in the patient representation, this foundation model itself up. One is actually reasoning. I think that's really what's going to help. We are starting the projects at the very moment to work on that. And agentic AI was also mentioned in both previous talks. I think it's the hot topic for us. There's a close connection for us between agentic and reasoning, because building this large foundation model, actually, if you look what is happening inside, there's a lot of agency itself. And somewhat they are very closely connected. So a very good reasoning foundation model, if you look inside, is almost like an agentic model, just not collaborating with the outside, but with itself, so to say. Yeah. So what are the compute requirements for evaluation and validation? There's luckily not that intensive yet, but we have this evaluation framework that we open sourced and is being adapted also by our competition. I think that's a really nice development. And so what this evaluation framework is designed for foundation models. So foundation models it's hard to inspect what's going on in this patient representation. So you build a lot of downstream tasks. Some are useful, some are not less useful. But every time you do a change in your foundation model, all these downstream tasks in the evaluation framework, they get retrained and then benchmarked. That's the way how we see that we're actually doing improvements in the model itself. So it is this retraining and doing this constantly is also quite compute intensive, but luckily it's not in the hundreds or thousands. The deployment again into the clinic, I didn't spend much time on that, but of course that needs to be super secure. There's you want to have these pipelines certified, and we expect that to build once we have this really good patient representation with lots of tasks, then it's going to be 3 to 5 nodes in a large hospital to actually serve that clinical AI assistant. And so if you scale that with, say, 50 or 20 to 50 hospitals, then we're at around 100 GPUs for our inference parts. So to finish my talk here, so where are we? At the moment, we are in the hundreds. Number of GPUs. We can do the vision pre-training. We have some first projects into post-training, the reasoning part that I explained. So we're moving there quickly, but that's also, I think, where we're stopping. So we don't. Of course, the AI development's going to be really fast. We don't know even what's going to come up tomorrow. Maybe this picture changes, but so far we see, okay, it's clearly, I mean, you cannot compete with the big ones, or put it the other way around. We are so happy to just have that LLM building block into what we are building to jump on these exponential developments that are happening there. But then building this around, we want to own, and that's basically doable with around 1,000 GPUs. Thank you very much.